Good. Okay, so autocorrelation, the topic for this morning's lecture. Okay. I think I know what it is. I need to start again. So first of all, we want to ask ourselves, what is auto or self-correlation? Remember one of the previous examples that we looked at yesterday, we had this irrigation water salinity data set, and that was inversely related with surface soil temperature data. And we had quantified, good morning. Oh, good morning. Yeah. Good morning. At this data set of soil temperature data, surface measurements with an infrared gun, and irrigation water salinity level. And we had seen both variables were inversely related, and that relationship was quantified, the shape of it, with the regression equation, with an intercept and the slope, and with a coefficient of determination of whose square root, so that is then a negative number, is the correlation coefficient, the Pearson correlation coefficient. So these two variables we learned were correlated with each other. Now we have to ask ourselves the question, how can we autocorrelate a set of observations? Remember, I walked yesterday down here several times, this pathway, and in every tile we had taken one measurement along the line. And now we want to relate these measurements with each other. And you will certainly ask, how is that possible? How can I correlate an observation with each other? Must be 100%. Yes, correlated. If I correlate this observation with itself, then we get a perfect 1/1 line. So that is right. That's a coefficient of 1. But now we want to correlate observations from another perspective. So we do not correlate this observation with itself, but we correlate it with the next neighbor. And then we take this variable now being, so to say, the y variable, and we correlate it with the next one, that is then the x variable, that is separated by the same distance as the first pair of observations. And so on, we go down the whole way here, and I have a little cartoon on that, what I just showed you here on the tiles, but you get the idea. So we correlate observations that are separated by a certain distance called lag with each other. So we want to answer, after this session, we want to answer the question, or want to become able, what can we learn from the autocorrelation function? And how does it depend on data fluctuation? That's the important thing. So early in my career, when I was a young scientist in Germany and we got a new boss, one of his questions was, well, he had to ask something. One of his was, how do you justify your measurements? How do you evaluate how good they are? And my simple answer was, well, I check their autocorrelation function. What I meant with that answer, we want to learn in this lecture now. So how does it depend on data fluctuation? And what are relevant questions related to this method of data analysis? So first of all, we want to go here into a little cartoon of measured data, sampling a spatial process, what to learn from spatial covariance. So here, like the set of tiles down here. Imagine now we have 84 tiles. Here they are 50 centimeters away. They are here, these field measurement points were 1 meter away from each other. And these data collected pH value by my colleague Luis Carlos Tim, who is a professor in Brazil. 1998, or a little later, no, sorry, 1999 and 2000, he was with me working as a visiting graduate student in Germany at that time. So he brought these 84 sampling points, and I think they are a wonderful example to demonstrate what I want to tell you with this data set. So here, again, the typical visualization of one-dimensional spatial data that were collected along a transect. On the x-axis, we have position in meters, and on the y-axis, we have the pH value. So this looks very simple to you. What's the big deal with it? I want to remind you, I've seen it very often. People spend a tremendous amount of time in the field or in the lab collecting their serial data along a transect or time series data versus the clock or calendar. And then they start running statistics. But the most important thing is that you first plot the original data. Many people think that's obvious, and they think from looking at a table, a list of data, they know how they look. No, visualize them. When you look at these slides that I'm showing to you, the most important information is always the behavior of original data, because that kicks your intuition. That will stimulate you to go in the right direction with a further analysis. So we want to do that, start with this here, and over the next days have many examples of these. Also, I want to point out to you, it is very important that you have good quality figures. Why are you sitting in the statistics course listening to that very common thing? Well, I'm a journal editor, and I see a lot of manuscripts where the author spent a lot of work on analysis and writing, but the figures are really terrible. And I want you to not do that. If you have badly presented data, then you bring the reviewers and the editors right away up against you. So please keep in mind, use readable numbers. So have appropriate size of label fonts and text fonts in the figures and also in regions. And Excel always gives you these default settings. They have a figure title up there. No, there's no figure title. What we have to say in a figure in a publication is written below it in a caption. So keep that in mind. If you have good figures, then the reviewers and the editors and later the readers will really appreciate your efforts, sharing with them your information in the best possible way. So these are the pH data, and let's keep the shape of these data in mind for now. This data set was collected in a field in Brazil in 1998. The next data set that we are looking at here, also sampled by Luis Carlos Tim, was pH values a year later in 1999 in the same field at the same locations. So you can see, or we all can see, that the shape of these two data sets appear to be relatively similar, right? Slightly higher values here, then some fluctuations, a valley here, and then again up and then down in the right-hand side. So next, we run an ordinary statistics analysis, something that you have done before and that you are doing and that everybody would do who collects data like this. So here's a histogram for both types of data, and you see the number of classes that I've chosen, more than the recommended. So we had 84 data, so normally 9 classes would be fine. I've picked a few more. And this histogram was calculated with a relatively old package from Deutsch and Journal that's called WinGSlib. It's still online, freely available. It's a very good geostatistical package. No further supported, but it's very straightforward and helpful. So these data, both data sets, because samples were taken at the same location, we had 84 observations, and the mean value in year 1 was 4.76, and in the second year was 4.86. Well, you who have experience with pH measurements, you would not consider that a dramatic difference. From 84 observations here, you get 4.76 there, 4.86. We can easily say, oh, that's roughly the same. Their standard deviation is 0.29, 0.28, and the coefficient of variation 0.06 and 0.06. So very similar statistics, right? And the maximum here in year 1 was 5.6, 5.6. The upper quartile 4.9, there are 5, median 4.7, 4.8, lower quartile 4.6, 4.7, minimum 4.2 and 4.2. So what would you say about this analysis? Here again, these numbers larger. So what would you say about this? Give me your judgment, please. Now you become the teacher of the short course and you tell the students what you think about these two statistics. Mean and median are very close. Yes. Yeah. Normal distribution. Yes. What else would you say with regard to both years? I step aside. Variation is similar, yes. Yeah. Okay, here's my statement, my conclusion from these two data sets. Both data sets yield almost the same results. Sampling once had been fully sufficient, either 98 or 99, right? The second year of sampling did not bring any news. Could have saved a lot of work. So Luis Carlos could have spent his time in better, more efficient ways. You always know that only afterwards, right? That's great. But wait a minute. Now we want to give a closer look to both data. But before that, I want to expose you to the questions that we want to be able to answer after this lecture. Are the measurements spatially correlated or are they spatially independent of each other? That's what we want to learn. Right now, it's a little foggy, but after this lecture, you will know the difference. Are the measurements temporarily correlated or independent? So we deal here with a spatial data set, but it can be projected to temporary data as well. How large an area does a single measurement represent? Or how large a sample should I take? Over what time period does an observation hold? This is comparable to this, just projected in the time domain. Or how often should a sample be taken? Is there a relation between sample size and autocorrelation length? You don't know the term yet, autocorrelation length. We will all learn that. If measurements should be taken again, what improvement should be possible in terms of changing the sampling intervals? So once we have done all the hard work, we think, oh, how can we be more efficient next time going out to the sampling? If small treatment plots are contemplated, what should be the minimum dimension of each plot for a meaningful analysis of variance? Remember that assumption of independent observations. How large should the sampling domain be, or how much does the resulting autocorrelation change with increasing the sampling domain size? So whether we look only at, for example, 40 points in that series, or at all 84 points, that will make a difference. Remember the scale triplet. Any component changed causes a difference in the result. Is there a relation between sampling domain size and autocorrelation length? And how does autocorrelation length for the spatially referenced variable change in time? So here, my little cartoon, or first of all, the display of it. So here is that layout, and our index n is equal to 84 sampling points in this example. You remember very well the equation for the Pearson correlation coefficient, right? So this one is very simple. Now we write here r, and we have a little as a function of, behind the r, as a function of h. And h in this case is called the lag. Lag, lowercase h, or the lag distance. That is the distance, I should have brought my ruler here, the distance between two sampling points. So here it is 50 centimeters. That's h, for the shortest sampling distance between these points. In the field study with pH, it was 1 meter. So for h, we divide the covariance between the measurement taken at x and x plus h. So that's the covariance between this and this point, and then between this and this point, and then between this and this point, all summed up and somehow, and then we divide it by the product of their sample standard deviations. Sorry, population standard deviations. We will do that this afternoon in a computer exercise. So then you will exactly know what we do with this equation and with these. That's obvious. And this covariance, the numerator in this equation, is described here. We will work with this equation this afternoon in an Excel spreadsheet on a data set, and then get the covariance. And well, we will also learn to calculate this coefficient in R, but I want to expose you also to 1 or 2 lags that we calculated on foot. So step by step. And that way, we better understand Fisher, the famous statistician from Rothamsted, who knew about spatial variability, but he could not put it into reality because, well, the mathematics of this is not at all complicated. It's very simple, but it's so many steps. And Fisher didn't have Excel, a spreadsheet, or Fortran where he could easily run a loop, or R where he could do that. So he had to come up with a second best alternative, or best alternative. So that's the reason why. So no complex, difficult mathematics, but a lot of calculation steps. Let's keep that in mind. And here also remember, we are basing this on n, so for the population variance, not on n, not on n as a function of h. The implication of that, you will see in another example. You may first consider it cheating, because when you average these squared difference product, or not squared, but these difference products, you do not really average them. So for that, you would need to divide this by the number of classes. When we have the shortest sampling distance, compare just next neighbors, the number of pairs is n-1. When we go then to the next step, so compare this one with this one, and this one with that one, then we have n-2 pairs. So with increasing lag distance, this n would be, or n of h would be smaller and smaller. But the statisticians say, oh, you keep it with n. And that's for two reasons. The one reason is the developers of these time series methods, statistical people, engineers, who work with thousands of data on time series analysis. And they would not look at, like we in the field, where we have just merely 84 samples here, or even less than that, 60, 64 in that salt and temperature example. So for us, every observation counts. For those engineers, since they have thousands of data, they say it doesn't matter whether we divide that term by 8,000 or by 7,999. We are anyway only interested in the first 10, 15 legs, 20 legs. That's what the engineers would say. The rest of it is not relevant for us. So they took it kind of sloppy. On the other hand, I must say, and we will see that in the example, the advantage for us is if we take n, we automatically make the denominator, or make this value smaller. We decrease. If this is large, this term will be smaller and smaller with increasing lag distance. So it obtains a lower weighting than the short lag distances. So with increasing lag distance, we will have less and less and less observations. I know that's a lot of stuff, but I want you to start thinking in that area. I will have an example where we go through that, where we see the shrinking number of pairs, but n remains up. So the large lag distances are not so meaningful because we don't have so many pairs. And this is an elegant way of having a weighting coefficient, so to say there. You had a question? Okay. Let me ask you, so can I repeat that with another example? And if that does not become clear, then I will repeat what I just said. Okay, good. So equation simple. So here now we go through this exercise, and this saves me jumping from tile to tile here. So we have h equal to 1. And what we do with that is we plot this value versus z. So here we are in h equal to 1 in that scatter plot. We plot the first one, which may be this one, versus that one. And then the second one is maybe this one versus that one. So we plot them, and then we calculate the correlation coefficient for this scatter of pairs. And the first correlation coefficient that we obtain is 0.8. We now get that 0.8 value and put it into this graph here. And this is the autocorrelation function. On the x-axis, we have lag h, the distance between samples, and on the y-axis, the magnitude of the autocorrelation coefficient. And that magnitude, you know, is between -1 and 1. Here it is plotted only between 0 and 1, but theoretically it can be smaller than -1 and can be larger than 1. Now, I'll explain this one in a moment. Now we go to h equal to 2. We have this cartoon here, and now we plot this observation versus that one. Then we go to point 2 and plot this versus that one. And, oh, I have a pointer here. And then we go to observation 3 and plot that one against observation 5, and so on. You see already we have fewer pairs of n, or fewer pairs of observations. And here in this case now the correlation decreases. We come down to 0.6, and we then draw this point here. So what does that imply? With increasing distance of observations from each other, we see their relationship becoming weaker and weaker. Does that make sense? I think it is. We can intuitively get the idea quickly. The closer observations are together, the more similar they have to be. And so on. And we go through an example in a moment with those temperature data. But I want you to get the idea of this schematic here. Now in this diagram, you also see a curve, this one. That is a very simple nonlinear autocorrelation function, which is described as R as a function of H is equal to R0. That is the autocorrelation coefficient at 0 lag. And then in the exponent, we have minus lag distance over lambda. Lambda is the so-called autocorrelation length. It's a coefficient, and based on this equation, we know that 1 over E, or that lambda is the length, is the magnitude of or lambda is computed for the length where the autocorrelation coefficient becomes 1 over E. So it is 1 over 2.72, which is 0.37. And where this value is 0.37, we go over, and this is then lambda. So for this data set, the autocorrelation length is about 3.8. What 3.8? 3.8 lag intervals. We have two choices of dealing with the x-axis in our calculations. We can use lag intervals and then count 1 lag, 2 lags, 3 lags, and so on. Or we take actual distances. We can replace this axis by the actual distance. We would then write from one tile to the next at 0.5 meters, 1 meter, 1.5 meter, 2 meters. It's your choice, but after you have made your choice, you then need to adhere to whatever you use here. We have in our mind, for our tiles, H is equal to 0.5. For the pH data, H would be 1 meters. So that's totally up to you, what you choose. R0 is equal to 1. Why is that? Well, of course, as we said earlier, if we get to any point here along this line and we correlate it with itself, it's a perfect fit on the one-on-one line, 1 by 1 line. So any observation correlated with itself has to give the result 1. Okay, any questions so far?
Can we use the definition of this autocorrelation length? So it is
okay. Yes.
The lag at which the correlation coefficient becomes equal to 1 over E.
Yes, exactly. That is the autocorrelation length. So thank you for repeating that. So Professor Kotari said the autocorrelation length is where the autocorrelation coefficient becomes 0.37. That is 1 over E. That's lambda. And we can derive that from this equation here. This exponent function, of course, you know, is R of 0 times 2.72 to the power of minus H over lambda.
Autocorrelation becomes 1 by E.
Yes, 0.37. And we consider that, and that's a very pragmatic approach. We consider that as the limit from where on observations are not dependent anymore. This function, so at any sampling or any sampling interval below this length, we have structured variability, and any interval larger than lambda, we call it random variability, unstructured variation. But I also want to make you aware or ask you that you do not get too fixed on this function. This is just one function. It does not describe the autocorrelation behavior for any data set. It is just one very pragmatic, simple function. How would you obtain lambda? You have a data set, you have pairs of data. On the first column, you have the lag distance beginning with 0 and then 1, 2, 3, 4, and so on. And in the second column, you have your autocorrelation coefficients. Now you fit this equation to it and you optimize lambda. Have you worked with optimization? How would you do that? So we will use an R routine, but we will also learn how we could do that in Excel. Do you know solver? The option in Excel? Okay, we will use that at several points in this course. So we will also do the autocorrelation fit using the optimization routine within Excel solver. It's a very nice, simple tool. Now we want to go into the soil surface temperature data set that we looked at yesterday again. Excuse me. And we want to run autocorrelation analysis on this data set, and I take the result that we will be obtaining up front here. This is the outcome. So it has nothing to do with that nice decaying function. Here in this case, we see ups and down in the autocorrelation function. That is to be expected because the original data have cyclic variations. They go up and down. You remember that layout design from the salt level of irrigation. They could not randomize those salt irrigation treatments. They had to put them out in a certain particular pattern because they could not put, for example, a high salt level next to a plot with a low salt level. There would have been a huge concentration gradient in ion concentration and salt concentration that would have caused diffusion right away. So they had to go stepwise from high over medium to low concentrations and then have jump always over 2 steps, and that they get down and then back up again. And then the next block begins with the replication. So that was so to say, a circular pattern of treatment. That will keep us busy in the second last and third last lecture when we talk about spectra analysis. So what I want you to remember here at this point, that the shape of the autocorrelation function, especially if the original data are cyclic, the shape of the autocorrelation function represents the shape of the original data. So now here's the example that we want to go through, and I hope this works with the animation. So here, this is like in my little cartoon, this is the temperature at point xi and xi plus 1. So the temperature value here and the next one. And here's the data set. And we open up the window. So this is the first lag window. Start here, and the window is 1 lag. So we plot this value versus that one. Now we got the train going. So with each, it automatically. Okay, then I do it manually. So when I move this window ahead, each time we get a new point here. You see that. So that's always the one versus the other plotted here. And we create this diagram. And since we have 64 points, you can see, or you get the idea that how many points will we have in the final diagram? 64 points. And how many pairs will we have in this diagram? Well, you know the answer, 63. Okay, now next, we calculate the line. And for the first leg, we have an autocorrelation, or we have an autocorrelation coefficient of 0.34. Next step is, this is the same graph that we saw in the previous slide here in this part of the figure. We now start plotting the autocorrelation function here. And I do not let it begin at 0 because I know the results. So I've started at minus 0.5 and let it go up to 1. So this first coefficient I put in here. That's the autocorrelation coefficient for leg 1. Everybody on board? Good. So now we go to window 2. 2 legs. So now I need to do the tile jump again, and then go back to that, and then that one. Okay, now the animation works automatically. So the window of 2 legs is moved automatically over this whole data set, and each time we add another point to it. And you can tell me now also how many pairs of points or pairs of data do we have in that diagram? 62. Yes, very good. So this is now for the pH data, h equal to 2 meters, the separation distance, or 2 legs. So we come to an end here. Okay, it's complete, 62 dots. And next step, the computation of the regression line. And now we get, again, 0.34. So we put that also into this diagram. That's the graph. And we put the second point here. Not much different from the first one. So that is for leg 2. we don't go through these windows. I think you got that idea. Now we look at the different legs. So we see with increasing lag, now we are at lag 6 and come to 7. Now this correlation gets even negative. So the slope is inverse directed. Lag 9, and after 9 lags, it will then begin to increase again slightly. So let's follow that. Lag 11 already, yeah, it's still down here in that valley. Now it goes back up. So the correlation, the autocorrelation becomes again positive. We will look at the original data in a moment to understand this. How can the autocorrelation be negative? Now it is more positive again. We get up to another peak in a few legs. Yeah. And now, lag 19, it becomes small again. So first an up, now an increase, and then with further increasing the size of the lag window, it gets again negative. Around 0, and now slightly negative and more negative again. And after 27 legs, the correlation begins to increase again. And soon we will get to another maximum that is not quite as high as the first two maxima before the correlation becomes smaller again. And we go to another negative valley here. And in a moment, we will have passed the next low zone, and the correlation will again become larger. We are now at lag 47, so we have only about 17 more legs to go. Comes positive again. Now fewer and fewer points in each diagram, because we have only a limited number of pairs that are a long distance away from each other. That's why n decreases with each leg by 1. So it goes up. And then again down. Oh, still up a little and then down. Yeah, now it goes down again. So like 58, 59. 60. That's a small correlation. I would say it should look higher than that, right? And here's the last leg. So you can tell from that, well, 2 points, if we correlate them and we calculate the R square for it, it should be R equal to 1. because that line is the direct connection. It's not the case, and it is not the case because of n in the denominator is still being 64. So that covariance, in the covariance calculation, that term in the numerator is divided by 64, not by 2. Had we divided it by 2, it would become way larger. It would be 1. So this is the result of this analysis. Oh, and what I just said, I have put here in the equation. So this is the equation of the covariance. This term remains 64 for each leg. And we add the final one, that is R at lag 0. That's up here. It's 1. Perfect fit. I want to go quickly back to a few slides ago. This one. So that we understand why the autocorrelation is negative. At a certain distance here, around 9 lags, we get into a minimum. And that is because of, we can count from this point 9 positions ahead, and then we are somewhere up here. 2, 3, 4, 5, 6, 7, 8, 9. So a low value versus a large value. And this one versus the next one. And if we count from that maximum, the next 9 values, we get to a low value. So that creates the inverse behavior. In that pair of calculations, 4 lag equal to 9, we always plot a high value versus a low value, whether that is on x or x sub I or xi plus h, doesn't matter. So that's why we are here in a valley of low correlations. And then when we come up to 18, if we count from that maximum value, 18 positions ahead, we get to the next maximum. Or here, from this low point, 18 positions ahead, we get to this low value zone. So we always pair, or if we imagine this is a cycle, then 18 lag distances is one complete cycle. And we always find, if we count 18 positions ahead, we find the same or similar position on the next cycle. It plays the similar role there. So that is how these cyclic variations occur and how they are manifested in the autocorrelation function. Does that make sense? Or do we want to stay with that for a while and reiterate it? Good? Okay. So then we move on. But please understand this textbook shape of the autocorrelation function from height and then to decaying, and this lambda concept is a general universe form of the autocorrelation function. And that's good. I'm glad we have also these cyclic behaviors. Where do they play in nature an important role? Well, in daily weather data, temperature, in fluctuations in the soil. So we will look at those data. Microbial respiration in the diurnal wave behave like that, or also in an annual wave. Everything is cyclic, fortunately. It comes back, pendulum.
So this distance, did you have multiple treatments and that is causing the cyclic behavior?
Yes. For that, I will quickly go back to the set of slides that we looked yesterday. And so I can quickly switch between presentations, right? And and still share my screen in it, right? Okay, I can try at least. So I first need to get out of presentation. Now, is this slide in the shared screen? Yeah, good. Okay. So thank you for pointing me at that. This is the pattern. So here, our 64 observations are in this direction. So we begin here with 1 and then all the way down to 64. And we have only plotted for one replicate. Otherwise, it would be a too crowded screen. This is replicate 2. Here we had these different levels of salinity in the irrigation water. And here's what I explained earlier this morning, that they could not put a treatment of 6 right versus 1.5, which was the lowest value. They had to go with a not too extreme deviation from 6 in order to not cause too much of a chemical gradient, of a concentration gradients of salt between two neighboring plots. That would have caused smearing in the behavior. So they put the next second one. So the treatments were 6 and then 4.5 would be the next. But they said, okay, we take 4 here and then let 4 follow with 3, which is also not too different. And then 3, let that be followed by 1.5. So here's also a small increment. Then here is not so much, but a larger increment to 4.5 and then a next larger increment to 9. And they repeated this same pattern. They had no chance to randomize this. They had to do this for chemical reasons. So they put this replica up there and there and there. So they have, so to say, 4 sine waves. And those are the 4 sine waves that we see in the original data. Okay, here. 1, 2, 3, 4. That's the behavior of salt level. And I can show you the spatial layout of those soils. If I find it. I need to leave this briefly to look it up. Here, this slide. So here we see what I just showed here in that direction. Here we see these different levels of salt. And don't be confused about these 3 points. These are 3 points within the same plot. The point distance for temperature measurement was designed in a way that they had 3 temperature measurements within the same plot. So, and the salt level was uniform within each plot. And then they get to the next level. So starting with 6 and going to 4, followed by 3 and then 1.5, going up to 4.5 and then 9. And then again the next wave and so on. Okay, so that cyclic behavior of treatments imposed a cyclic behavior of the soil temperature values. Thank you for reminding me to clarify that. Thank you. So we have answered this question already. What is the autocorrelation length? That is the distance across a landscape characterized by an individual observation. So lambda. In that case, of that cartoon it was, where it was 0.37. So this is the end of this little cartoon, and now we go back to our pH values. So don't forget, for the sine wave behavior in the autocorrelation function of temperature data, we cannot identify a correlation length, lambda, because the shape is cyclic. And the nature of data is different. We can answer a lot of more questions with a cyclic behavior. We don't need to worry about the autocorrelation length so much. The nature of data is just different. So we now go back to the pH values. And now we want to look at, again, at their similarity, which was indicated by the ordinary statistics. And we now compute the autocorrelation function for these pH data. Here is for the data set of 1998. So 0 lag, of course, autocorrelation 1, and then we have a decay in the autocorrelation function, going to 0 at some lag. Here, in this example, we would say lambda, well, 0.37, lambda would be about here. So at this lag, up to this lag, pH observations are correlated with each other. That's for 1998. Now let's look at the data for that the autocorrelation function computed for the 1999 data. Similar statistics or identical statistics, mean, median, and so on. And the autocorrelation behavior is completely different. After one lag, we drop right away down to 0 for the rest of the series. So no correlation, except for lag 2. We will look again at the original data in a moment to see why is it everywhere 0, but at lag 2, we see some correlation here. Unlike the first series, where we have relatively smooth behavior in data, except this part, and this part of the series, we can always see that the fluctuations from point to point are smaller than the overall fluctuation. For year 1999, the point-to-point fluctuations are way more present in this data set compared to that one. And here now you can see why we have at lag 2 such a large autocorrelation, whereas at lag 1 and 3 and the rest of the lags, it is so small. So if we go from this point to that point, there's a large difference. But if we come to the second point from this one on, it's the same observation. Or if we start from this point or that point, we go up here and then we come down, or here. So it's a zigzag movement. And the second lag distance showing us a large correlation reflects just that zigzag behavior, which is not inherent everywhere, but in many zones within that transect. Okay? So that causes that different pattern. And that's why I said earlier on the slide, wait a minute. So now we want to get into the next step and say, how do we communicate about this different autocorrelation behavior? And you interrupt me at any time when you want me to repeat something. So this form of behavior, we describe it in a class or in a paper. We call it spatially structured, where we see a clear decay and then decay at 0 here. We call it structured, or we say the data, the observations are spatially correlated, or they behave spatially continuous. So only slight differences from point to point. Overall, there is variation, but point to point, it's continuous. It's like you go down a stairway and there's a handrail, and overall there's a change, but it's very continuous. The stairs go down and the handrail goes with it, so no big fluctuations. It's continuous. And this behavior reflects representative behavior. So each point, if you go to that 0.37, earlier my information was wrong. I had here 0.2. So I said up to this leg. No, 0.37 is here. So up to 4 legs, any tile. So if I go to this point, 1, 2, 3, 4, up to that tile it represents, and back 1, 2, 3, 4, it is representative for this distance. Or I can go to this one, where the data can have different magnitude, but again, this one represents up to that tile and back to that tile. So remember that this x-axis in the autocorrelation function has nothing to do with position at the transect. It is just the relative, or it is just the distance between points. That's important to keep in mind. So what are the implications of this behavior? What do you say about that data set? Well, yeah. Which data? Yes, exactly. You are ahead of me. So with that upper example, with the 1998 data, I would say I was lucky. Well, I say lucky because you don't know in advance how your data turn out. So following his intention, Luis Carlos Tim did the right thing to sample every meter, and he got a nice data set where the observations varied in a structured way. And once there's variability structure, then you can use that data for spatial interpolation. You could then use it even with a nice function that we will learn about later between those 2 points. If you are interested in the behavior at the point at any location in between, you can interpolate it because the data are not fluctuating randomly, but structured. And this would give me the answer to my former boss that I've put out here a few minutes ago. What do you do? Data quality? I say, this is good data. They are not fluctuating randomly. I've somehow was lucky to hit the right combination of the 3 scale components: domain size, distance, and volume of a sample. They contributed to this behavior of data. It doesn't say that this is the end of the story. It doesn't answer what would happen if I had taken smaller volume or larger volume of samples. Doesn't give an answer to that. Or what if I had not sampled 84 meters, but only 30? Or 150? Doesn't give an answer to that. We can, though, say, we can easily throw out observations and say, what if we had sampled only 1, 3, 5, and 7 legs? So that's the implication. A good way of doing quality control. We are not fishing in a random pond. We have structure, like in that fever curve from yesterday that we talked about. Now, how do we describe this variation? And I want to point out, don't see this as a negative, as a result similar to ANOVA. When you don't get significant differences, you open your desk, put the data in and say, oh my gosh, I did the wrong thing. And what a mess, no significant differences. I had worked for it so hard and I was expecting a difference so terribly, but it didn't turn out. Well, there are so many things that can cause that, but never take that as the end of it. Go to the next step, show that you are bright and you can deal with that information. So here, first of all, I say how we describe it, and then I say what I would do next. So we call this variation, we call that behavior spatially random, or we say the observations are spatially uncorrelated. They behave discontinuously and they are just strongly fluctuating. The implication is no interpolation. That is what I use always as a reason to say, please do not use inverse distances for making maps, because inverse distances produce you a map for such data. You just hit the button and the computer will put you out a map, and if you change the exponent in the equation, it will put you out a different map. So do first a good quality control and only interpolate those data that you find spatial structure for. Then interpolation is justified. And if you present a map that is based on random data, if you present that to decision makers of environmental policies, you can cause a lot of harm. So be conscious about it. Only use good data for making spatial assessments and predictions in scenario analyses. An example of that is yesterday's lack of relationship between total porosity and hydraulic conductivity. No wonder that there was no correlation. That's the effect, and I think it is Mother Nature's sake and blessing for us that it is more than total porosity that affects hydraulic conductivity. But don't use derived from somewhere derived bulk density, convert that to porosity, and then convert that into conductivity. It will not give a physically sound or biogeochemically sound map. So we want to know also how significant is this relationship. We can calculate confidence intervals for the autocorrelation function with a very simple equation that's also given in that book. So the probability P divided by square root of n. That gives us a straight line. I will show it in a moment. And then we have also a rather comprehensive equation consisting of this as a product, and then we have this equation that includes the process of autocorrelation behavior with increasing lag distance. The result of that is demonstrated here in a paper by Morkoch, who was a PhD student with Dr. Nielsen and who was one of the first who did these analyses in 1985. So here were data on irrigation level. They had taken sorghum yield perpendicular to high and low salt level of irrigation water. And then they came up with the autocorrelation function for this data set, which is shown here, the bars, autocorrelation versus lag. And then they computed, so these were the correlation coefficients, and then they computed with that second equation these confidence intervals. So only up to two legs, the correlation was significant, and then it fell below the confidence limits of the correlation function. This illustration is a little difficult to follow. I've other ones that we will look up next. So that is the confidence interval is not a constant. It will change with this equation. We will use this equation also in Excel when we have the autocorrelation function calculated. It's a relatively simple calculation. Here, an example for, again, the 140 soil water content measurements that we looked at yesterday. You remember that we did the histogram and the fractal diagram on these data. Now we have done here the autocorrelation function, and we get a lambda of 3.3. And we can then, afterwards, we can calculate still the confidence interval. So what would you say about this fit? How does that line fit the autocorrelation coefficients? What's the requirement of a fitted curve? A curve that, a curve that is fitted to experimental data. What is the requirement? When would you say that fit is appropriate, suitable, good? I'm sorry. Please repeat it, and a little slower. Please repeat it, what you just said. I could not hear you. Can somebody repeat it for me? I'm very sorry. My ears are extremely bad.
R-square value tends to 1.
R-square value should be 1. Well, yeah. Okay, that's for simulated data. No, so no, the R-square value should be as large as possible, right? Yes. Okay. So what else? What is the requirement for a good fit? More points?
On this line or curve, then you can say it is a best fit.
Yeah.
The distance between the point and the line should be less.
Yeah. The error should be at minimum. Yes. Yeah. Have you ever read, when you read an article where in the statistics part of the materials and methods, they said, oh yeah, well, this fit was zero mean uncorrelated. Have you read those words? Zero mean and uncorrelated. So what does that mean, that statement? Let me explain. That zero mean part means that if we average all these deviations from between measured points, or here, the experimental autocorrelation coefficients and the curve, those average to 0. Furthermore, uncorrelated, they refer to autocorrelation. So they refer to that statement says that the deviations between points and the curve are random. They are uncorrelated. Random means one point would be above, another point below, and so on, fluctuate. Is that given here? You could now you can calculate the deviations, in this case, between the point and the curve, and then run an autocorrelation for those deviations. Would they be uncorrelated? No. Why not? Because here in this range of lags, all deviations were that the points were above the curve. Here in this part of the curve, all the deviation, and for all the deviation, it's valid that the points are below the curve. So that is really not uncorrelated. That is strongly correlated. There's a trend in the deviations. Do you understand that? So the fit gives us, and I have no doubts that this is the best result that you can come up for this curve. But we could not write in it that it is uncorrelated. No. The curve is not ideal. That is what it says. You need to be critical with that. I would not mind publishing this and then say, well, for this equation, we couldn't do any better. But if you are really eager, for example, if you have a series of modeling results and you see that there is for some time in the simulated series, there's there's an obvious behavior that, or a systematic deviation of measurement from simulation above and then later below. Again, that is not a negative. We should take it for thinking, well, here in this part, the model is inadequate. Something happens, and we should take that to improve the model, to bring that, to remove that systematic deviation. And it's always better to have deviations that we can look at to learn from it than just having it scatter. So that's, of course, then perfect, but we can learn more from it. So this would tell us this equation is not the ideal one for that data set. So why I'm telling you that, you can project that to other problems of curve fitting. And now you know what it means when they write in their paper, zero mean uncorrelated. Deviations are zero mean uncorrelated. Any questions to this point?
What's the relation autocorrelation and stationarity when we are discussing the spatial data? Actually, we deal with a lot of raster data. So we come up with the stationarity.
Yes.
We have to deal with stationarity always.
Mhm.
And what is this relation? Because there also we see this lag length and all this thing.
Yes. So here is a comment that also goes ahead on stationarity. Do we have a few more minutes, or if we get to the next block, then a few more hours? I will talk about stationarity, and I tell you up front, I don't have an answer for you. So stationarity is difficult to handle, and I decide that we have to live with it, and I will show you some examples. Because it is terribly difficult to say for a data set whether it is stationary or not. So we have now learned about several shapes of the autocorrelation function. And here's a general schematic where we look at different shapes. And in their behavior, whether it is here we see A, that's an autocorrelation function that drops very steeply. So that comes closest to a random data set. And then we have type B, and that is a little smoother. We may see some structure, or more than in curve A, we may see some structure here. And C shows us that we really have a strongly structured data set where we have sampled close enough to follow up fluctuations in the data very well. It can be, we can observe this different behavior for the same variable, but in different fields, in different years, the same field, different variables, and the same year, and so on. And if we even wipe out here the scale of lags, Well, no, we can use the scale of lags. We have not said here anything about metric distances or distances in meter. I would describe the 1988 data with this curve, C, or pH data. We could have made that data set easy type A if we had taken samples only every 4 or 5 lags. So, do you understand that? So it depends on the sampling. This is not only the nature of the process, but this is a reflection of the quality of the sampling. Soil surface temperature data here in the east-west direction. So where we average out all those fancy treatments. Very small standard deviation, mean 6.63. The autocorrelation function is shown here in this graph, and the lag distance is already smaller, or the lag distance 0.37 is below 1 lag. So that data set is random. We cannot do any spatial interpolation with that data set. And it does not show cyclic behavior because the cycles were X'd out. We look at a different direction of data. Bless you. Another example of groundwater boron concentrations sampled every 8 meters here along almost a kilometer distance. The autocorrelation function reveals a correlation length of 42 meters. Again, see here with our simple equation, R equals to e to the power of minus h over lambda. Again, we have some systematic deviations in different parts of the function. We could have also used the polynomial to fit that, but the polynomial does not allow us to define lambda easily. Yeah. Soil water storage in a 75 centimeter deep soil profile measured over 105 days with evapotranspiration and 14 irrigation water applications. So you can count these here and here, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then 14. So here we have daily measurements, and the autocorrelation looks like this. Now we go to a scenario where we, in a temporal domain, where we have not a sample every day, but every few days. In the next slide. And here we have measured it only on a weekly basis. So these are those measurements, weekly now. Oh, this was daily, and weekly is here. Same data, we have just removed observations. And for the daily data, the autocorrelation function is here. And for the weekly data, we have missed the part of structure in the data. So here now the data vary randomly in time. This is the typical situation that you end up with when you make decisions. It may work out well, you may find structure, or you may not. But you have something in your hand that will tell you the next step. And here I want to give you one more point of guidance, how you can distinguish. Namely, there are two reasons for unstructured variability behavior in your data. one reason can be, so this is like in this case, it can be time, or it can also be space. And here you have high values and low values, and you have huge fluctuations. And your points are not taken dense enough in the data set that you could identify a structured correlation, but they would end up in random fluctuation. That can be one reason. A second reason can be take a different pen here now. A second reason can be that we have only slightly high, and here we have only slightly low. What I want to say with that is that these differences, these fluctuations, are becoming very small compared to the variation, to the sensitivity of our instrument, or compared to the overall variation of the process. For example, the first one, from high to low, could be in the scenario of an irrigated field. You have huge, due to high crop evapotranspiration and maybe seepage, you have big fluctuations in water storage. The other one could be in a rainfall scenario where you have fluctuations, but the changes, or the soil may be just with a young crop, not much evapotranspiration, or even a bare soil, you just have small fluctuations in your original data. Well, you want to show all those ups and downs, and that's why you make that y-axis scale wide to make them visible. But in fact, the differences are small. And then your autocorrelation function ends up in a random shape. And the autocorrelation function will not tell you which of the two reasons caused it. You have to bring here your expertise, your understanding of fluctuations in water contents or storage in the field in order to say, oh, if those fluctuations were just 10 millimeters over a sequence of a week or so, 10 millimeters is just a little more than a diurnal evapotranspiration. That's not much of a fluctuation. Whereas when you have 40 millimeters, you say, okay, that is substantial. That is 7 days of evapotranspiration. That is a magnitude. And if I have not covered that with my sampling, then I need to sample more frequently. With those small fluctuations, you can take 7, 10 samples in a day, and you will not get a better result because the fluctuations are so small. So that's why you need to look at your original data and get an idea to now make the decision, okay, I go for more frequent sampling, or I don't worry about all these minor fluctuations. I just need to sample over a longer time to get into a period where the fluctuations become larger due to incoming rainfall or to suddenly starting crop evapotranspiration taking up. So that's why I said you need to bring your science, your disciplinary knowledge. That's important to now make the next decision. How do I sample from here on? So this can as we just learned from this example, this can manifest rapidly occurring processes. They manifest smaller correlation lengths than slowly ones, or these processes can also be just minor. Now I want to get back to the scale triplet here, and we want to look at the impact of sample size on the shape of the autocorrelation behavior or function. Here is a soil surface, and we have preferential flow paths in this soil. You have all seen those in the field. And here we go back to this example of having just distinct measurements. Every little wiggle is covered with our sample, or we are in the field where we have a certain sample volume and we may catch the process or not. We may catch the fluctuation or not. Or also with these tensiometers here, do we have the sphere of influence covered or not? So if we have the sphere of physical influence is 0.6 as opposed to lambda equals to 5.5 meters, that's the statistical sphere of influence, we conclude then that the given nature of the process and the degree of heterogeneity at the scale studied, the magnitude of autocorrelation length depends on the sample size. So converting that into this example, here we ask, do we observe preferential flow with our respective sample size? And we use two different sample sizes. One sample size is small. These are these red dots and many, many more points. These are the small samples, and we have applied a tracer that have moved rapidly downward, and we now apply on a trench profile that we opened up. We put in these cores at regular intervals, and some might hit the preferential flow paths and others do not. So here we do not find the tracer. Oh, first of all, do you understand what I want to illustrate here? Good. So with this small sample taken here, we do not observe the tracer. Here, far away, we do not observe it. Here, we do not. Here, in this case, we see it. Again, here, no, here, yes, and also at some distance, yes. So this small volume would be causing this steeply dropping autocorrelation function. And we would not observe a structured, spatially continuous data set. Have you ever taken soil cores in the field for undisturbed samples? Yes. So how would you do that? You start with the uppermost layer. The way I do it, then I remove a little bit of the surface, depending on from how deep. And then what would be when you are there and you look at the surface, what would be a criterion for you where you insert that core? Go to here or go a few centimeters over? What would be a criterion? You have made that decision. You have seen it and you wanted to make the best qualified guess to use a good spot for the core. What would drive that decision for you? Yeah.
When you take the sample out, it should be uniform. You see the uniformity.
And no stones in it. Yeah, no grass roots poking out and so on. And when I collect samples for hydraulic conductivity, I have a hard time because my farmer is a no-till farmer, and I cannot find a spot where there are no earthworm channels in it. He has tremendously high saturated conductivity. So then the next good thing is what I could do is that when I take a sample, I don't have 3 or 4 earthworms. I just go with the same number of earthworm channels. What would be a good approach is to have larger rings and then take them over an area where I have covered the representative elementary volume. So here with this, apparently the correlation goes down. No structure. Now we sample with the larger volumes, these blue boxes, larger sample. And what's the answer here? So yes, we got the tracer here. We got it here and here and here. So we find it everywhere, and the autocorrelation function of the results of this is much, much smoother. So that's this one component, the sample volume in the scale triplet affects the result of the autocorrelation function. That's why I said yesterday, if you change only one component of the scale triplet, your statistical result will be different. Another example, infiltration measurement with infiltration rings in the field. We have these small, tiny ones. We insert them in the ground, and then we pour water on it. And if we are good, we have a little Marriott device there to keep the water head constant, and then observe infiltration rates. Can do the same also with larger rings, and we can have them even overlap. So in that first case, small samples, we may catch a point where we have an earthworm in it, or no, or yes. So anyway, steep drop in the autocorrelation function. If we have a larger ring, then the spatial variability, so this is not only statistically, but also physically overlapping, and that causes a much smoother correlation function. There's one very good paper in Soil Science Society of America journal. I forgot what year it was. I used it in my soil physics class, where a PhD student working under Eileen Kladivko had made systematic analyses of this in, I think it was 1 square meter plots. And he had used, it was a tremendous amount of work, different volumes of cross-section, surface cross-section, and then determined how the variance and the spatial behavior changed for different volumes and different areas. That's a very good paper to read, how such an investigation can be done in a systematic way. So same sampling distance, but different cylinder sizes cause different autocorrelation length. Curve 1, C1. So the effects of local distribution and lambda of a state variable depends on physical, chemical, biological processes in the past and at present. Here, the solute migration and reaction. Curve 1 shows, for example, ammonium in solute. So it's highly mobile through diffusion processes. And curve 2 is ammonium on the exchange complex, not much mobile at all. It's more sorbed there, and changes in the micro scale happen much, much slower. So the values are more stable and causing a flatter correlation behavior. Soil surface temperature, we have gone through that example. And remember, yesterday we had looked, this might be an outlier, and this, and this, and this. Now we know already better. Those fluctuations were caused by the treatment, and these extreme values are part of a process. So don't act too fast on extreme values. They might be part of the process rather than being an error. Autocorrelation behavior here, completely different than this smooth, characterized by the curves ABC or C1 and C2. Here we have this fluctuating behavior. And the shape of the original data is manifested in the correlation length. And giving us this peak, we can say, regardless where we start walking and counting in this process, if the next peak is at 18, then I need to walk down 18 tiles, and then I will have a value that is very similar to the one here. And if I walk down only 9 tiles, then it will be a value much different than this one. That's manifested in this autocorrelation function. Here, frequency distribution and spatial relationships. Soil water content, the number of observations. Water in the soil profile measured on a daily basis. And this is the autocorrelation function for the water in profile. So what more does give us spatial and temporal relationships compared to just merely focusing on the frequency distribution, looking at mean and variance and whether they are normally distributed. So this describes the total population and the observation of a probability of an observation with respect to P. We just ignore the coordinates. That's what it says, in other words. If we ignore the coordinates, we can just make a general guess of what the probability is that at this point or any other point, my observation will be so-and-so. If we look at spatial temporal relationships, we do not need to know the frequency distribution necessarily, but the autocorrelation function for the total population will tell us the local probability of what an observation will be. So if I know the number here and number there, then I can make a good guess, a better guess than just from the frequency distribution because of the local neighborhood. Who of you has worked ever with pedo transfer functions? You know what that is? Anybody who wants to explain what a common pedo transfer function would be? We use existing soil information, for example, soil information from a database, and then we compute soil hydraulic properties, saturated conductivity or dry bulk density, or the Van Genuchten parameters. You know those from the retention curve. Those parameters describe the shape of the soil water retention curve. We can derive those from pedo transfer functions. Alpha, N, and so on. That's fine. That is not more than a regression, so to say. You know Rosetta, perhaps. That's a very modern neural network pedo transfer function. What we miss with the pedo transfer functions, a very good opportunity that we not only take clay content, sand content, dry bulk density, soil organic matter into the estimation of those properties, but if we take into account what's the property next by. That spatial component added to pedo transfer function would really be a fantastic change. A former student, Shi Zhang, has used an approach, a mixed pedo transfer function, regional probability type. And that's a good approach to give better estimation quality to these Peter transfer functions. Okay, so now we had 2 hours. Ready for a break? Yeah. So afterwards, I want to ask you what you learned this morning, and then we want to give a brief repetitorium, what you learned or what you did not understand maybe before we continue. Thank you for your attention, for the good discussion, and for being alert. And then we meet in 30 minutes again. Okay?